To calculate the quantities of this electrical circuit, you first need to know series circuit laws, the Kirchhoff law for series circuit. You also need to know the laws for Kirchhoff's law for parallel circuit, because now we have them combined. Now, looking at this circuit, we have a 50-volt power supply. Current is going from top to bottom because we know the short bars are travels from negative to positive. We have load 1 and load 5 that are in series with the source. Look, there, load 1 is connected to the negative terminal. Load 5 is connected to the positive terminal. So R1 and R2 are in series with the source. R6 is in parallel with the source. R2 and 3 are in series with each other, but in parallel with R6. So here's the trick. When working a series parallel circuit, you must first condense this complex circuit into a series circuit so we can calculate IT. Once we calculate IT, we're going to work this circuit just like it is, okay? So this is the first step. The first step is you got to simplify so you can get your resistance total. Then, we got voltage total, so if we get resistance total, we'll have two pieces of our pie, and we can find IT. Then we'll be able to know how much current is going through here, how much is going through here. We'll calculate a voltage drop, and the remainder will go to the parallel branches. So here we go. If you know how to do this, you're good at series parallel circuits. Alrighty. So first off, each other. So first I have to rewrite that circuit. I got R1 parallel with R6. So now what I've just drawn is this. This here is R2 comma 3. And we know that they're in comma 3 is 600 ohms. Hopefully everybody gets that. These are in series, so we add them up. So 100 ohms. It is in parallel 3K ohm resistor and in series with the 1K ohm resistor, R5, and R1, 50 ohms. So now our next step, we went from here over here. So now we got to get it because we want it to be a simple series circuit so we can get RT. All right, so now we know that RT is in parallel with RC. You do either the reciprocal or the product sum form. The same answer. So we're going to calculate 3 comma 6. That's letting me know that these are in parallel with each other, okay? So do the product sum. So if we did the product sum says so here we go. 600 times 3K. Let me put my ohms. Divided by 600 ohms. So if I do the math, okay, 600 times 3 exponent 3 for 3K is equal to, that's a big number. Positive 6 is mega. So 1.8 mega ohms. All right, so if I did 600 equals 3,600 ohms. So should be 1.8 exponent 6 divided by 600 equals, it gives me 500 ohms. Okay? Now, the reciprocal formula, just to show you all that we can use either formula and we're still going to get 500 ohms. The reciprocal formula says R2, 3, 6 is equal to 1 divided by 1 over R2, 3 plus 1 over R6. So if I put those numbers in, I got 1 divided by 1 over R2, 3 is 600 ohms plus 1 divided by R6 is 3K ohms. So we're going to put that into the calculator and I'll show you that you're still going to get 500 ohms. So I clear it out. So I'm going to do 600 shift reciprocal plus 3 exponent 3 shift reciprocal. I must hit equal shift reciprocal, 500. So it don't matter whether you do the reciprocal or the product sum, you still are going to get an equivalent resistance of 500 ohms, okay? So I'm going to erase that. We know that R2, 3, 6 is 500 ohms, okay? So I'm gonna go from here and I'll draw the next same circuit. We're just simplifying it so we can find RT, which will allow us to find. So now we got R1, 250 ohms. We got R2, 3, 6, which we calculated to be 500 ohms. And we got R5 here. R5 is 1K ohms. So now that it's a simple series circuit, I know you all can calculate RT. Kirchhoff's law says RT is equal to R1, in this case, plus R2, 3, 6, plus R5. And if we write those numbers down, we have 250 ohms plus 500 ohms plus 1K ohm. So I'm going to calculate that and get our RT for this simplified circuit. So we have 250 plus 500 plus 1K. 1 EXP3 equals. It gives me 1750, 1,750 ohms. Okay? 1,750 ohms for RT. So I'm going to write up here our totals. So we know VT is 50 volts. We just went from this big circuit, simplified it down to a series circuit so we can find RT, which was 1750 ohms. So RT is equal to 1,750 ohms. So now we can find IT is equal to VT divided by RT. 50 volts divided by 1750 ohms. 1,750 ohms. So we're going to find our current total. So put in your calculator, 50 divided by 1750 equals. It gives me a decimal. You can use the decimal, but I like y'all to use it in engineering notation. So the calculator will do the work for you. You hit shift divide, and it gives you the number in engineering notation. As I've said in class, in lab, if it gives you something more than just a plain number, I want you to use the 2 digits beside the decimal. So in this case, our current will be 28.57 milliamps. That -3 lets us know that it's milliamps. So 28.57. And the reason why we leave 7 is because it's a 1. If that was a 5, we would raise that 7 to an 8. So our total current in this case is 28.57 milliamps. Hopefully everybody understands that. 28.57 milliamps. So we did all that work, and guess what, you guys? We're not finished. So went from this complex circuit down to a simple circuit just to calculate RT, but now we got to go back and from scratch. Okay? We did all that to find our current total. So bear with me as I erase this, because now we need our columns. Now, what's the voltage? Here we go. Same as I've been telling you. Say, okay, I'm going to write my columns. We got R1. We know that's 250 ohms. I don't know my voltage, but I bet you I know my current, and I'll explain that in a minute, okay? So that's R1. Then for load, we'll do R5. R5, because I'm going to start with them first. We got a 1K ohm resistor. We don't know the voltage drop. We got our R5. We got some current. Okay? And then for R6, that's the one in parallel. We know the ohms. We don't know the voltage, and we don't know the current, but we'll figure that out here in a minute. And then we got load 2. Load 2 is 100 ohms. We don't know the voltage, and we don't know the current. Look like we don't know a lot, but we'll figure it out. And then I'm going to write R3. They gave us 500 ohms. We don't know the voltage, and we don't know the current, but we're going to figure that out, because now we know Kirchhoff parallel circuit. We also just calculated our current to be 28.57 milliamps. So here we go. R1 is the source. So all my current, once my current leaves this parallel branch, all of my current, and R1 gets all of my current because they're in series. So R1, we know our current to be 28.57 milliamps. Why? Because it's in series with the source. R5, we 28.57 milliamps. So now we can calculate the voltage drop for these. We calculate that voltage drop on the parallel side. All right, so VR, we know the formula, Ohm's law. I voltage, my formula is I times R. So it's IR1 times R1, which is equal to 28.57 milliamps that we're going to multiply by 200. See what that voltage drop at R1 is. So here we go. 28.57 EXP3, and I'm going to change it to negative because it's milli. Multiply that by 250. I get a voltage of 7.14 volts. Why? Because that 2 will not raise that 4 to a constant. So we got 7.14 volts. 7.14 volts for R1. All right, so let's find the voltage drop at R5 because we have to simplify. So VR5 is equal to IR5 times R5, and that is equal to 28.57 milliamps that I'm going to multiply by 1K ohm. Here we go. 28.57 EXP3, change it to negative because it's milli. We're going to multiply that by 1 EXP3, positive 3, because 1K is the same as 1 exponent positive 3, equals, we got a voltage drop of 28.57 volts. 28.57 volts. Alrighty. So now you got to look at it like this. We got 50 volts. I drop off 7.14 volts here. I drop off 28.57 volts here. The remainder of my 50 volts goes here. So let's see how much we have remaining. All right, so I'm going to do 50. I'm going to subtract VR1. VR1 is 7.14. So minus 7.14 equals, 50 minus 7.14 equals, I have 42.82 volts. 80, I'm sorry, 42.86 volts. Now I'm going to subtract VR1, VR5. So minus the 28.57 volts that drop off as R5. I'm left with 14.29 volts. Parallel circuit. So this one here, this branch is going to get 14.29 volts. And guess what? That one will too. That one would get 14.29 volts. Why? Because parallel circuit, Kirchhoff says VR1 is equal to DC. So if all my voltage left is 14.29 volts, then both branches will get that. Now in this case, R6 is going to get that whole 14.29 volts. But R2 and R3 will split that. How much of the 14.29 volts does R3 get? All right, so one step that we know we can do right now is because we can do this. We know that R6 is getting 14.29 volts. I just want to double check that. Let's see. So R1 is getting 7.14 plus R5 is getting 28.57, so 28.57 equals, and then I'm going to add 14.29 plus 14.29. 7.14 plus R5, 28.57 plus what's going to the parallel branches, which is 14.29 equals my 50 volts. So my 50 volts is being ate up by all the resistors. We can calculate their voltage drop, okay? So knowing that our 6 is getting 14.29 volts, we can calculate that current, okay? So here we go. IR6 is equal to, I'm looking for I, so my formula is V over R. It's VR6 divided by R6, which is equal to 14.29 volts that I'm going to divide by my 3K ohms, and we're going to calculate that current. Here we go. So we got 14.29 volts that we're going to divide by our 3 exponent 3 equals. I get 4.76 milliamps. So the current going through R6 is 4.76 milliamps. Now think about it. Kirchhoff's law for parallel circuit says that IT is equal to IR1 plus R2. So in this case, if my total current is 28.57 milliamps for the entire circuit, if we just calculated this one to give 4.76 milliamps, the remainder goes over here. Hopefully you're with me by now. So if we got 28.57 milli and we subtract 4.76 milli, it's going to leave me with hit shift divide to get engineering notation. I got 23.81 milliamps. So over here I got 23.81 milliamps. That's going to go down this branch. Right? So if that current is actually going down, this current here is going through the branch. We know that R2 and R3 are in series. So I can go in and write. I know that this one is getting 23.81 milliamps. I know that R3 is in series, so it's getting 23. Use my handwriting. 0.81 milliamps. So we can calculate how much of that 14.29 volts is going to R2 and how much is going to R3. So here we go. VR2 is equal to IR2 times R2. That is equal to my 23.81 milliamps that I'm going to multiply by 100 ohms. Let's see what we get. 23.81 milli. Multiply that by 100. And that gives me 2.381. So I'll say 2.38 volts. So we got 2.38 volts. Off top, if I know I have 14.29 volts coming down this branch, and R2 gets 2.38, I can automatically tell you, let's see, 14.29 minus 2.38 equals 11.91 volts. VR3, I'm going to write it a little bit under it. So VR3 is equal to IR3 times R3. Let's see if we get 11.9. So we got 23.81 milliamps. And we're going to multiply times 500 ohms. So put in my calculator. 23.81 exponent 3 negative, or 23.81 milli. We're going to multiply that by 500 equals, haha. It shows me 11.905. That 5 makes the 0 round up to 1. So we have 11.91 volts. All right. I know that was a lot to take in, but hopefully you all understand it now. First thing first, you must condense this big circuit, combine R2 and R3, get the equivalent resistance of that value with R6 parallel. Then add that value of 2, 3, 6 to R5 and R1, which gave us a value of 1750. Then that allowed us to find our current total, which was 28.57 milliamps. So now, talking it through, I'm almost done. We got 28.57 milliamps. All of it hit R1. R1 gets 28.57 milliamps. We know that it's 250 ohms, so we can calculate that voltage drop to be 7.14 volts. R5 volts. 28.57 and plus 7.14. So I'm going to 28.57 plus 7.14. That gave us 35.71 volts. And the remainder went to this parallel part. So parallel circuit, 14.29 volts going this way, along with going down that way. But we know that R6 is all by itself, so it's going to get all of that 14.29 volts. So with R6 getting 14.29 volts, we can calculate the current that it's getting. Kirchhoff's law, if you don't remember parallel circuit, adding up the branches. So if we know we got a total of 28. 4.76 milliamps is going to R6. The remainder, which is 23.81 milliamps, is going down this branch. But R2 and R3 are in 3.81 milliamps, and R3 gets 23.81 milliamps. That allowed us to add up VR2 plus VR3, which is 11.91, you're going to get the 14.29. Hopefully, I didn't throw you all off, and if you can work a series parallel circuit, that series Kirchhoff law down pat, as well as parallel for Kirchhoff's law. Look over this video, practice it. I highly suggest that you all draw down that right. Draw it from the top, how I started, and work it step by step. If you mess up, start back over. If you mess up, start back over. It's only practice for you all. So that's the end of it. And remember, if you wanted to calculate power, you can calculate power as well. Practice, 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 and remember, you can do it.